maybe. We'll see. There's at least one slide with some medical references to it. So, hello everyone. My name is Sarat Babu. I am in America, the Chief Executive Officer, or in the UK, the Director of a company called Betatype Limited. We have been around for the last 5 or 6 years, and we're here, predominantly what we're doing is around application development in serial production. So moving away from these kinds of singular cases where we're building, different parts every single time to how do you do that and build 1,000, 10,000, 100,000, 1 million parts with these technologies, and does additive, 3D printing as a technology, does it have a place in the kind of pantheon of manufacturing technologies and mass production? So I'm going to go through a couple of slides. We work predominantly, so we're a completely commercial enterprise. We don't really do any research work with institutions, or that's not our commercial model. We work with a lot of large-scale blue-chip companies across a range of different sectors, basically investigating what you would use additive manufacturing for, because there's quite a few different questions to that. Because why are you moving away from this new type of process to a completely new type of technology? Where is the value in that? And there are two major challenges. One of them is understanding how we can make better performing parts. How can we make things which kind of step beyond what we traditionally kind of envisage in terms of mechanical engineering and industrial design. And then the second part with any kind of emerging technology is actually how do you make a business case, which seems rather, kind of boring, but actually kind of incredibly critical, because, it's not enough for you to just have a technology which can create something new. It has to do that in a way which is economically feasible. And interestingly, a lot of how you do that, or how we do that, is actually around the way that we actually control those processes. And so as an organization, we're about 11 people now, and even though, as I said, we do most predominantly do services, we're actually split 50-50 around applications engineers, and then the rest is a software team, which builds all of our core technology, which is what we use day in and day out for service provision. So I've got the slide titled, What is AM? And that's slightly confusing because, obviously the talk is titled around 3D printing. So 3D printing actually, and all of the associated technologies themselves have a real identity crisis problem, because 3D printing actually is a specific type of additive process. And when I say additive, this is the process of building something up in part through layers. So 3D printing is a specific type of process. We heard about FDM as another type of process, but essentially this captures actually a whole range of different types of processes for lots of different materials, coming from plastics all the way to high-end metals. And additive manufacturing is a kind of ASTM agreed term for those technologies which are kind of actually entering into the industrial space, and are kind of qualified because they actually provide mechanical properties which are similar to traditional manufacturing. So this isn't, you're creating kind of similar materials. This is, we're actually printing in metals that we can use for all kinds of different applications. What's really interesting about additive manufacturing fundamentally is that it consolidates processes. What I mean by that is that, like, traditionally when we think about how we make something, first of all, we form the material. So, we're kind of creating the kind of the in this case, the metal or the alloy that we want to create. And then we have a secondary step where we actually create and form the object itself. And so the amount, this is almost how our disciplines in terms of engineering actually exist. You've got your physics on this side, don't have a slide for that one, material science, and then your mechanical engineers. And so what actually happens in additive is
value creation from a single 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 value creation from a.
So, some examples of parts. The reality is that actually there is a lot of manufacturing happening. It's not really publicly talked about because the main reason is we're talking about very, very high-end industries and markets. And this is usually driven predominantly by economics, so in terms of cost. So aerospace and then this includes both kind of rocket nozzles, as we have here on the left, and also civil aerospace. We are building, there's quite a lot of flight-ready parts on the space side. There's also a lot of applications in civil aerospace, and this is largely driven because in order to get these types of, to build these types of parts consistently, you would usually have to have multiple step processes to build them. So you would have to, first of all, take a billet, and then you would machine part of that out, and then you'd have to weld something on, etc. And that each of the qualification issues that come across that challenge mean that actually it becomes much easier to use a single step process like additive. And it's also very similar, actually, in the medical space. And this is an acetabular cup, which is part of a hip replacement. Companies like Stryker Orthopedics have produced probably at this point hundreds of thousands of these implants. And they are in use today. Here, we have a tremendous opportunity to actually design this porous structure. And the way that structure actually interacts with the bone is actually, can be actually engineered and designed in order to kind of promote bone growth. So there's huge amounts of, really exciting opportunities in the medical space around that. But as you'll know from that, just looking at that, there's a lot there. There's a lot of structure. There's a lot of data. When we think about these systems, our machines are actually, considerably smaller than the systems that Greg's talked about. So this block on the left is about 250 by 250 in the XY, and then about 300 mil high. It contains in that model around about 20 million individual lattice elements, every single beam here. And we can push those down to the order of about 0.1 millimeters, right? So you can already start to understand the challenges from the standpoint of how do I build a geometric representation of this model? More importantly, how do I take that geometric representation from a digital plane and actually manufacture that data? How do I build computational tools to help me deal with the amount of data that we're kind of pushing across? So there's actually this incredible richness in 3D printing and additive manufacturing for the application of really interesting algorithmic approaches to solving that, and that is part of what we do. But you also need to incorporate a lot of understanding across a whole range of disciplines. So there's still a lot of things that are unknown about like the way that the actual laser powder bed fusion process works, like what actually happens when a laser is fired and hits a bunch of powder, and how does it form that metal. Lawrence Livermore National Laboratory actually went ahead and kind of like looked at this with a low-speed camera, and it's definitely a really quite exciting video to watch as it kind of blows away all of this metal powder as it's focused down on a microscopic level. And actually watching the melt fusion interaction, condensation, it's an incredibly complex process. We're still very early stage in understanding that, but we have to bring some of that understanding into our design process in order to be able to understand, what works, what isn't going to work, in terms of, what actually allows you to build a good part. So part of what we're doing at this point is, it's kind of a bit too far ahead for us to start applying machine learning or AI to what we're doing. But what we are doing is building the environment for those algorithms. So what we're doing is we're building a lot of models and data to help us actually create environments where we can actually start to then bring more sophisticated algorithmic problem-solving solutions to that space. I want to give you an example of a case study of a part which is something I can actually talk about, because 90% of the projects that we talk about are on that level where you can't actually get into any level of detail. But this is a project which talks about a couple of those things that we did with a company called Uniform Wares, which is a small watch manufacturer here in the UK, but they're a global retailer, so they're selling product across the world. And what we worked with them on was developing a brand new material, and that material is actually in this watch, and it's actually the watch strap itself. So working very closely with them, we designed and manufactured a new type of fabric mesh, where we're actually kind of going through the process of trying to understand what the design potential of that could be, and how the computation side comes into that. So one of the things that we wanted to do was create a material with an asymmetric behavior, right? So as you can see, as I'm folding that fabric structure, what I'm getting is two completely different bend radiuses, right? You can start to see where this can have all kinds of different applications, from flexible hinges in consumer electronic devices to heart stents. But this is the kind of level of control that we're trying to achieve here. And to do that requires us to be able to model down into this part with a tremendous amount of detail. And this is, it's this kind of fidelity which is where the complexity really starts to lie. So in this actual weave itself, unlike normal kind of mesh straps or fabric woven, these parts are actually built where there is no weak link. It's a single link which is all intersectionally built. So that allows us to provide a very high level of precision in terms of a way of controlling that behavior. Each individual strap contains something like 39,000 individual elements, and we need to, from a CAD environment side, have the ability to go in and modify every single individual strut. Doing that allows us to do things that allow us to simulate, for example, how the actual behavior of that structure is going to work. So just by moving a few links around about 50 micron, we start to have the ability to physically engineer exactly how we're going to want that to behave in the real world. And that's, and this kind of level of control can then be exercised on an individual link level, which gives us a huge amount of customization, something that you just would never really be able to do with a standard part. Now, when I talk about like the kind of amount of detail we're talking about in each of these parts, it's important to kind of give you the context of what I mean by those numbers. So in the individual watch straps, and I have an example with me that we have, there are 35 million laser operations per strap. And in each operation, I have about 10 to 15 different variables that I can control in order to control the way that the actual melt pool and the physical process of fusion actually occurs. And I need to be able to control that. At the moment, this is happening at around about 10,000 laser operations per second. So that laser is moving in increments of up to 20 microns, traveling at speeds of around about 2 to 3 meters per second. And we need ways of being able to manage and control that data and be able to individually go into each individual operation and be able to manipulate it as is required from a design standpoint. So what we've done is built a lot of additional control and software levels of control in order to really be able to dig into that process and actually be able to manipulate and bring that level of opportunity to the table. And that is something I think which is a big component of where the future really sits with a lot of this technology, which is that we're seeing a huge amount of improvement in the systems themselves. Laser powder bed is probably the most predominant technology that exists today. It's industrially used by companies such as GE, as I mentioned before, Stryker Orthopedic, and a whole range of kind of aerospace customers as well. But we are seeing a whole new generation of systems coming out, and with them comes improvements to material quality, surface quality, and also productivity in these systems. But what we're tending to find, and what's really interesting, is that computation has become this almost universal language for us. So, you know, when you're working with designers who are typically drawing on a sheet of paper, how do you bring computation as a language into something which can work, you know, as flexibly with their requirement to represent something, but then can also be, you know, transformed into something with a huge amount of high level of specificity. And then being able to move between that translation of data. How do you manage that data? These are all like really complex and interesting questions, because we're not moving from someone like, you know, providing a drawing to a shop, which then machines it, and then someone then polishes that at the end, right? Like there's actually traceability in that data and how it's managed, and it really does, I think, have a really interesting position in also fundamentally changing. Not just physical manufacturing, but changing all of the kind of engineering disciplines as a fundamental aspect of it. And that is my short talk. Thank you.
Okay, any questions? Greg.
What do you think of these companies like Desktop Metal, which are building these fusion type systems? I mean, you probably know what they're actually called, but they're...
Every technology kind of plays a balancing act between the quality of the parts, the things that they can build, and the cost of those parts, right? And what we've tended to find is that laser powder bed provides us, it operates at multiple different levels. I think new technologies like Desktop Metal's binder jet systems will probably target quite different areas. So they will target slightly different, it's more comparative to metal injection molding, let's say, right? So smaller parts, higher detail, bigger volumes. So, and I think that's the thing, is that additive in itself is not going to be one process. It's going to be a whole range of processes. And actually, even within laser powder bed, what we're tending to find is that you would almost have different systems for different processes. right? So there's a huge amount of modularity, which I think is going to emerge out of these technologies. And they're not, regardless of the hype, they're not going to replace standard manufacturing, right? They can be an incredibly important part of that process, but they have a role to be, to play within that. And I think like how those technologies start to actually merge together, I think will be a key kind of component to this.
Thanks.
I think you partially answered the question I kind of had when you said that they're not going to replace traditional manufacturing.
Yep.
But are they not? I mean, not next week, but I mean, what do you see as the impact on? You touched on it. Traditional professions like engineering, and the social impacts of being able to manufacture stuff on demand almost, so it become a demand society rather than a supply society.
I think it's a revolution that I think would definitely be amazing to have, but it comes in a way which is probably not so directly comparative to the way that the Industrial Revolution changed everything, right? Because part of the problem is that quite simply, additive manufacturing parts generally aren't as good, right? And they're not as cheap. They're more expensive and they're worse 90% of the time, right? So fundamentally, a lot of people are going to be asking the question, so why bother, right? And economically, it makes sense, like in the high margin industries where, as I said, like when you're building a turbine blade for Rolls-Royce, you have a 10-stage process, and if you can knock some of those processes off, there's an economic argument. But we live in a world where we're competing with things on Amazon for £4 or £5. How do you compare? How do you make that technology stretch down to that level? There is opportunity, but we're also coming at a place where the manufacturers of these systems perhaps are less incentivized to have that revolution happen unless they're making a really big cut on the way in. So, there's lots of different like emerging components of this, which kind of are kind of fighting against each other. So, and the truth is that like, especially for civil aerospace, to get to real applications, it'll take 20, 30 years of qualification work. So there's a long way to go for certain industries to get there.
This is probably a question for not for the immediate future, but is there not a danger in combining 3D printing and AI in that you could have robots producing other robots and taking over the whole world?
Well, as long as AM stays where it is, then there'll just be very rubbish robots that come out of it. So maybe that's the end game and we play for that. Yeah, sorry, I didn't. That was that's not what I meant. But
What do you mean? Because you said before that the results of additive manufacturing are a bit rubbish. I presume people are using them in these safety critical scenarios. People are using your process in safety critical scenarios like aerospace, medical. They can't be that rubbish.
Well, to do an aerospace part is not just additive manufacturing. So there'll be the additive manufacturing, there'll be the post-processing, they CT scan every single part. I said that additive manufactured parts are expensive, but by the time you go through the qualification processes for those environments, it becomes a very small component of the cost. Similarly, the economics can also work in those environments where you can actually go through the process of qualifying every single part every single time, which is what companies like Stryker would do, which is insanely expensive, but they get major benefits from having a single process which consolidates lines. So, I mean, it's kind of sad that the main examples that you point to are all like just because the economics work rather than incredibly innovative parts. But I think that will start to emerge. As the other thing that we're really lacking right now is a huge amount of design and engineering expertise and how to actually utilize and take take advantage of these processes and design the next generation of parts. And that's actually lagging behind the technology. So we have amazing machines, but no one knows what to make with them.
Yeah, I mean, we struggle to find data on the material properties of printed parts.
Yeah.
Because companies don't really know what's going to happen after you print with a certain material.
Exactly.
Yeah, I thought I'd help answer your question about robots taking over the world, if you want. But yeah, I guess it's maybe conflating robots and AI. The robot is like the hardware bit, and the AI is the brain bit. So that doesn't answer whether they're going to take over the world or not. But just to be clear, the worries are sort of always around the AI being clever enough to eradicate us. But I presume that if it's cleverer than us, it probably doesn't need to eradicate us. We tend to try and eradicate ourselves, so we're definitely not very clever.
I have a commercial question.
Sure.
How do you find your customers, or how do your customers find you? Because if I understand you correctly, that at the beginning of the process, you cannot really guarantee the quality of the result of your process. So how do you manage that commercially?
The majority of our customers are coming from two sectors. They're either very experienced AM users already, and so they are coming at us for a subset of capability. So sometimes they're just wanting us to help them control the process, for example. But another range of our customers are completely, they don't know anything about AM, additive manufacturing or 3D printing, and frankly, they don't care. Where they are is they have pushed to the limit of what they can do with traditional processes. It's left them at a place where they just can't they can't push the design any further, and they're looking for a way to get past the competition. They're looking for a way to create new intellectual property. They're looking for a way to be ahead of the curve, and we've found a lot of customers in that process, because they'll have they need help the whole way through that process of, what can I do with this technology? And then how do I even scale that into manufacturing? How do I build a factory with these systems? And they'll need support all the way through that process. So, commercially speaking, we have, a handful of companies that we've been working with for the better part of half a decade, and helping them to build up that capability. We're growing with them, and in terms of cultivating their expertise.
Cheers, thanks for that. From your presentation, it seems like the state of the art is very niche still and very high end.
Yeah.
Do you ever see a point where 3D or 3D printers or AM printers are ubiquitous and have a low entry point? So people with personal printers that are user friendly, and people can use them to manufacture their own personal goods.
I really hope so, but it's a challenging environment commercially for a new machine manufacturer. Fortunately, some of the patents are starting to run out, so this creates a lot of competition. But I don't want to get into the dreary reality of a lot of these early adopters that built these metal AM systems. They didn't really traditionally build. They were just plastic machines where they just stuck a 200-watt laser in. And then they accidentally started making metal. And then someone still was like, oh, we can actually build parts with this. So they're coming at it from a place where some of this technology was developed 20, 30 years ago, and they've been sitting on these patents and kind of very variously protecting the IP around that. And that's led to a lot of stagnation in specific development and creation of cheaper, lower cost systems, which would start to really change the game in terms of the economics. And I think there is definitely a space for this, for smaller systems. Part of the challenge with powder processes is that obviously they are dangerous. Powdered metal is explosive, and that can go very badly, very fast. When you're handling, especially reactive materials like titaniums and aluminiums, we obviously have safety procedures and material control that we do on site. This is hardly the kind of thing that you want to be spilling on your kitchen tabletop. So there's going to be restrictions in that. But there are processes which are promising the ability to use metal powders without having to deal with like the actual powder itself. So it's embedded, and that's what the binder jet technologies are kind of providing. So fingers crossed.
Do you use a standard CAD package to make things like the extremely detailed watch strap, or do you develop your own software for it?
So on the pipeline side, we use standard CAD packages that we've adapted with our own plugins in order to, for example, deliver different representation types. We then have built our own software for translating those CAD representations into the actual manufacturing data itself in order to have full transparency of that process. So yeah, I mean, essentially most of our processes is built by us.
Great. Well, we've hit 8 o'clock. We've learnt some things. And there's a whole lot more we want to learn. Please firstly join me in thanking Sarat and Greg. Okay, closing remarks. Couldn't resist it. I was reading a Gartner report. It's a Gartner hype cycle about 3D printing. And it says here, metal 3D printing is on the rise in 2019. By 2020, 3D printed metals and alloys will become a critical element in supply chains for replacement parts in commercial, military, and even some consumer markets, according to this report. 3D printing and the medical sector, we've seen the medical sector make growing use of additive manufacturing, and now we know what that means. By 2023, how do they predict these things so accurately? By 2023, 25% of medical devices in developed markets will make use of 3D printing, according to Gartner's prediction. This prediction is concerned with the shift towards the use of 3D printing for pre-surgical planning and in performing joint replacement, surgical implants, and prosthetics, as we discussed earlier. However, some obstacles are very likely to arise, and as well as the ones we've heard about just now, ethical debates and regulations, where I guess BCS will be playing a key role. Still within the medical field, the third prediction is by 2023, 3D printing using biosynthetics and living cells will drive a multi-billion-dollar prosthetic and organ patch and replacement market. Wow, so we won't be talking about just software patches by then, we'll be talking about organ patches. Is that scary or what?